Okay, so let's review this example one more time, okay? Because it's been a week. So we said that when we have a moving rod, okay? When we have a moving rod, metallic rod, in a magnetic field, and that magnetic field is static, okay? So it's not changing by time. It might be changing with the space, but it doesn't matter. As long as the rod is moving, hi Avery. As long as the rod is moving, then we are going to have something called an electric field that is caused by this motion, okay? Which we call EM. And that EM can kind of produce the voltage difference VM here. EM is equal to U cross B, which depends on the velocity vector and the B vector. So here, we said the first method we can use was to go directly to the, let me just bring it here. We could have gone directly to the definition of VM being the time derivative of psi, okay? And then psi was defined by B dot ds here, where S is basically the length of the rod multiplied by where the distance x naught is as the rod is moving, right? That would show you how much magnetic flux you have through this area. But this area is a function of time as well. We said if x naught changes with ut, which is the velocity multiplied by time, then if you multiply that by the length, you would get the area. So we could have said, okay, Vm here is basically time derivative of this function where x naught is changing by time. And I think Muhammad helps us to get through this answer, which was what we were doing was basically time derivative of B naught L x naught squared over 2, right? Where x naught here is a function of t. X naught was a function of t. So we did all of this to get Vm is equal to B naught L U squared multiplied by t, right? Lots of trouble, right? Because we just learned that we could model this movement and the Vm that is being created by that EM, the motional electric field, let's call it, EM, right? This motion introduces or produces an electric field inside the rod, and that electric field introduces Vm, produces that voltage difference. So the second way we can do this is to say Vm is V1 minus V2, and then here, for example, this is 0.1, this is 0.2, then, or the other way, this is 0.1, this is 0.2, and then we just take the derivative, the line integral of EM, which is U cross B. Remember that this formula of the voltage difference, this is from the first part of the course, right? That voltage difference is equal to minus E dot dl. We plug U, we plug B, and then we said dl is always dy y hat. The only way that we find the polarity of Vm is by the bounds of the integral. So we get to exactly minus B naught L U naught squared T. So again, Vm is changing by time, and it should be, because as the rod is moving, the magnetic flux through the surface is going to increase linearly, which will introduce a Vm that is changing by time linearly. And you can compare the two solutions. The second method is much easier than the first method, which shows us the motivation behind that EM or electric field that is caused by the motion, right? It's kind of like an auxiliary way to find Vm easier, basically. Any question from this example? Yes.
Why is VM defined as like how do we what is VM defined by? Like which terminals is it defined by? Like in general.
When you say what, do you mean like 1, 2, 4, 3 compared to those, or?
Like, yeah, how do you know which terminals VM is at?
So it should be across the rod, okay? So VM is produced on the two sides of the rod, okay? So for example, here it's going to be 4 to 3. Then this is the VM we have, which if you follow it, you would see V1 minus V2 here, this is going to be, as I shown here, this is going to be the negative side, this is going to be the positive side, making the current going up through the resistor. Does that answer your question? So remember that the VM is produced on the two sides of the two points of the rod, and then you just follow that through the circuit till you get to the resistance. Let's solve more examples of this motional VMF. These are all examples of motional VMF because it's a motion that is causing it, okay? Do you remember what kinds of VMF we had except the motional one? Transformer, exactly. We had two types of VMF. One caused by motion, VMF motional. The other one was transformer VMF that was caused by the time-varying magnetic field. If the magnetic field is changing by time, that would produce some transformer VMF. Just different namings so we know the source. Okay, so here it says the current, the wire shown carries a current I equal to 10 amp, and I'm going to just assume this is to be I, so I don't have to calculate this numerically. And 30 centimeter is the length L of the metal rod with a constant velocity U in Z hat direction. I'm going to call this U naught Z hat. We are asked to find V1, 2, where 1 is closer to the wire than 2, okay? So here, let's use our motional electric field, EM, to find V1, 2. So V1, 2 is V1 minus V2, which is minus EM dot DL. And remember, the convention is that 2 comes here in the lower bound, 1 goes to the upper bound. The voltage that is getting subtracted is going to be lower bound. Now, let's find EM, which was U cross B. U is U naught Z hat cross B is B naught. Oh, what is B? We don't know B yet, right? We have to calculate it. Do you remember what is the B of a wire carrying current I? No?
It's like
Ampere's, wait. Ampere's law. Do you remember how we calculated the magnetic field of a wire using Ampere's law? Anyone? What would be the integral of JDS? This is
DS would be like the circumference, would it? Or it'd be like that would be a circle.
J.ds is the current that passing through that contour, right? So it's going to be the current I. That's one side of the Ampere's law. What was the other side? H.dl, right? So if we calculate H.dl is I here, then we would find that H is I over 2 pi r phi hat. Right? Try to remember this magnetic field of a current, okay? Yes, go ahead.
This is for P, I think there's a mu missing.
Exactly, thank you, yes. This is H, and then we multiply this by mu. So this is going to be mu I. Okay? Now, let's plug, well, let's simplify EM. This is going to be U naught mu I over 2 pi r. Z hat cross phi hat. Remember our circle, r hat, phi hat, z hat in cylindrical coordinate system. What is z hat cross phi hat? Negative r hat minus r hat. And this negative matters. Okay, so now we found this. Now we can rewrite V12 as minus mu u naught mu over multiplied by I over 2 pi r minus r hat. What's happening to this? Minus r hat dot dl when we move from, when we are on the rod, is going to be dr r hat. Remember, when we calculate dl here, when we want to write dl, we don't consider the direction. It's always going to be positive dr r hat. We take care of the direction by using the right bounds here. So at point 2, which is here, what is the distance from the current? Let's call this one R naught, and this is L. So point 2, how far away is it from the current?
R naught plus L.
Plus L. And then point 1 is R naught. Antoine, did you have a question?
Can you repeat how DL is dr r hat?
So let's look at EM, okay? EM is minus r hat direction. EM is basically in this direction, which says it goes from point 2 to point 1, okay? And I want to take the linear, calculate the linear integral of EM dot dl, okay? I'm saying we always for dl, consider positive side of the axis, and then take care of the direction of where you're going by the bounds. If you put a negative here, because you're going from point 2 to point 1, this would be a minus dr r hat, and you already put this in the bounds, so they're going to cancel each other out. Always for dl, put positive of the axis, and then take care of the direction by the bounds. Okay? Okay, so this is going to be, I have a minus behind the integral and a minus in r hat. So this is going to be u naught mu I over 2 pi ln of r naught over r naught plus L. Is r naught over r naught plus L more than 1 or less than 1? They're both positive numbers. Less than 1, okay? So this is less than 1. What would make the ln of this number to be? Negative, okay? So that means V12 is negative, which means V1 is less than V2. So this is positive, this is negative. And that makes sense because when we move in the direction of electric field, voltage has to reduce. So that's how we can find the polarity of VMF as well. Since this is a movement, I'm going to call this VMF motional. Sounds good? Clear? Yes, Mohammed.
DL is equal to DR only because it's like they're kind of aligned in this case? Not all the time.
No. Yeah, if you look at it in a cylindrical coordinate system, the rod is along the radius, is radially changing. That was a great question. Let's see another example, okay? Here, we have a loop. Inside that loop, we have a resistance R. And then we have, so let's read through this. The rectangular loop shown in the figure is situated in the XY plane, and it moves away from the origin with velocity of u0 y hat, okay? So the loop is going in that direction, away from the origin. And the magnetic field is static. It's not changing by time, but it is changing by space. It says By is in z hat direction, but the amplitude is changing with y. So if at the origin, this is Bz, or B in z hat direction, when we get to here, it's going to be a little bit less, and here a little bit more less, because it's an exponential of negative 0.1 y, basically. So exponentially, it would reduce. The amplitude of B would reduce with y. Okay? Now, it's asking, find the current I at the instant that the loop sides are at y1 2 meter and y2 2.5 meter. Okay? I'm going to solve this almost parametrically, and then not numerically, okay? So let's find the direction of EM first, okay? Do you have a question? No? Okay. So let's find the direction of EM. So EM is U cross B. U is U0 y hat cross B is 0.2 e to the minus 0.1 y z hat, which is going to be 0.2 U0 e to the minus 1 point y. Y hat cross z hat? X hat. Perfect. So EM is a function of y as well. So here, if I want to write this more accurately, I should write, actually, let me write it here. EM is a function of y. And it's in the direction of x hat. So this is EM. At both of these, on both of these two sides of the rectangle, this EM dot dl produces a voltage difference. And these sides, not so much, right? From 4 to 1, 3 to 2, EM, you can't find the voltage difference by E dot dl. We have to find another way to find the voltage difference between 0.4 and 0.1, okay? But let's take it step by step. Let's first find the VM that exists between 0.1 and 2, and the VM that exists from 0.4 to 3, because we have EM in that direction. V12 is V1 minus V2 minus EM dot dl, where lower bound comes from 0.2. What is the location of 0.2? This is 0.2. The difference between 0.2 and 0.1 is basically x direction, right? They're in the x direction. So 0.2 here is going to be plus L over 2. This is minus L over 2. So I'm going to write this as minus plus L over 2 minus L over 2. then 0.2 u naught e 0.1 y x hat dot dx x hat. Again, I don't care about the direction when I'm calculating dl. I'll just put dx x hat, just the axis. That is what matters. So V1, 2, both of them are in y1 location, right? Both 0.1 and 0.2 have a constant y, which is y1 location. So I'm going to put this as EM at y equal to y1, because V1, 2 is basically the rod is on the y1 location. So I'll make this one y1 as well. Now, this is going to be V1, 2 is going to be, there is a minus behind the integral. The bounds are minus L over 2, minus L over 2. So there is a minus L. So the minuses cancel each other. So this is going to be 0.2 u naught L minus 0.1 y1. Okay? Because when I'm integrating over dx, y is the only function that is basically has a variable in it, but the variable doesn't matter because it's not changing by x. So this is a positive number, right? Which again suggests that V1 must be more than V2, which sanity check, perfect, because EM is in the direction from 1 to 2, and it has to be V1 must be larger than V2, which is going to be here. Okay? Now, let's do the same thing for 3, the other side of the rectangle. If we do that, then V43, similar to the way we did it here, is going to be minus the integral of EM dot dl. This time, though, the EM is going to be calculated at y equal to y2, which is going to be 0.2 u naught L E minus 0.1 y2. This is also a positive number, so V4 is more than V3, and the polarization of VM along the side of V4 and V3 is the same, is correct. Now, let's model this, see what we just found out. We found that this rectangular loop look like here we have V12 here, we have an R, and then 0.4 to 3 was also modeled by VM43. Here we have positive, and the other side is negative. If I want to find the current direction here, right, I need to find if 4,3 is larger than V21 or vice versa, right? Correct? Right? Circuit theory. If I want to find the direction of I in this circuit, I need to know which one of these voltage sources is the bigger one, right? So, now, let's look at V43 here and V12. Which one of them is bigger? Go ahead, Amjad.
I think V12 is bigger since Y1 is a lesser number than Y2.
Exactly. So, since Y1 is less than Y2, then minus 0.1 of Y1 is larger than 0.1 of Y2, which would make V12 to be larger than V43. And they're both positive numbers. So let's just do an example. Imagine this is 5 volt, this is 4 volt. Now tell me, what is the direction here? Is it going this way or this way? The current. This way? Okay. So I'm going to make this ground because they're both the same side. That would be, this would make this one minus 4 volt. This is minus 5 volt, right? So the current goes from more voltage to less voltage. So that would make I in this direction. Which means I, again, is going to be in this direction. So now if I want to find I here, what should I do? Go ahead.
Is it V12 minus V43 divided by R?
Exactly. So here we can say I is V12 minus V43 over R. The difference between the voltage sources over R. Does it make sense? Right? Okay. Are we good with the motional, the motion of the rod in the magnetic field? This is kind of the last example on that. Yes?
So there's a VF on like the horizontal portions of the wire of the loop.
There is a VM on the, you mean from point 1 to 4?
1 to 2. Yeah, so there's only from 1 to 2 and 4 to 3.
Yes.
Nothing from like 1 to 4.
If you consider that that part of the wire, right, doesn't have any resistance, then no, right? The only things that can cause VMs in a loop like this one is either you have electric field aligned with the wire that causes the voltage difference, like just the rod, like the rod or something, right? But here, if you go EM, which is in this direction, dot DL, from 1 to 4, it's going to be 0, right? So there is no voltage difference between 1 and 4. The voltage difference that makes this possible, actually, because you have two sources that are different in size. The only way to make this, these two connected to each other is to connect them with a resistance. So you can have a current carrying that voltage difference. Yeah. If the resistor wasn't there, then immediately you would have lots of current going from one source to another, breaking it basically, to make it a similar, short-circuiting basically. You're short-circuiting. Good? No more questions? Okay. Now, let's solve an example on the motional EMF. Okay? So in this one, I think we mentioned this before, that our VMF can have three sources. One is the time-varying B magnetic field, which is transformer EMF. Other one, changing area, which was this one. Changing area is similar to this one, which was motional EMF. And then the last one is the angle changing, right? Because we said VMF in general is minus d over dt of psi t, where this is minus d over t of b dot ds. And this is basically amplitude of b, amplitude of ds, cosine, the angle between b and ds. All three of these variables can change with time. B can change, amplitude of B can change by time, ds, or the area, can change by time, and then the angle between the two of the area, and then this one can change by time as well. But let's see which one of these cases we have here, okay? Here, it says the loop is rotating by the angular frequency of omega in a static magnetic field. That means amplitude of B is not changing. The loop also, the area of it is not changing either. It's always looking like a rectangular loop. The only thing is changing, that is changing, is the angle between B and the normal vector 2 area. Here, you can see that we call this angle alpha. So here, this is going to be cosine alpha, where alpha is actually a function of t. As it's rotating, alpha, the angle between the vector normal and that one is changing. Alpha t can be written as the function of t as omega t plus alpha naught. Okay? But since we are told that alpha is 0 at time equal to 0, that means this is going to be 0. So alpha t simply can be written as omega t. So I'm going to call this motional one, Vm motional, because it's the motion that is causing this. Amplitude of B, ds cosine omega t. Since the amplitude of B is not changing, it's not changing with time, I'll take it out of the integral and, okay, I'll take it out of the integral because it's not changing with the space. It's always B naught z hat, so I leave it B naught. And I'm taking out of the derivative as well because it's not changing by time. Now, what is left here is d minus d over dt of ds cosine omega t. Cosine omega t is not a function of the area, right? It's a constant over the area. So that can also come out of the integral, but not the time derivative. So this is going to be b naught minus d over dt of cosine omega t ds. The integral of ds is going to be the area of the loop, basically. So this is going to be b naught minus d over dt of cosine omega t multiplied by the area, which we call LW here. So this is going to be b naught a omega sine omega t. Does it make sense? So I changed. Why do we call this an electromagnetic generator? Because I had 2 bars, let's say. I had 2 magnetic bars, different poles. And then I started rotating a loop in between them. And all of a sudden, now, I have a voltage difference across the 2 sides of that loop. I can turn on a lamp here, actually. So let me just quickly show you something. Oops. I can do this. Okay, I want to show you. So you can see here that as this is rotating, and we call those circles brushes, this looks like a brush, DC motor with brushes, basically. And you can turn on the lamp by rotating it. As you're rotating it, though, sometimes it's going to cause the magnetic flux to increase for half of the period. For half of the other period, it's going to cause the magnetic flux to reduce. So that's why the current direction keeps switching between the two. Keeps switching. Once this way, once the other way. Okay? And if you really, really pay attention, you would see that it's it goes, the light of the lamp goes up to gets to its peak, and then it reduces. It goes up and then it reduces. So actually, what it's showing here is a little bit misleading, but it should go bright and then reduce the brightness. Okay, let's go back here. So we just created an AC voltage source by rotating a loop between two magnet bars. Now, what if we made this a little bit more complicated? What if the magnetic field wasn't static itself? Even the magnetic field was changing with time. Okay? We can have that too, right? Don't look at it. Okay, so this time we have the same loop rotating in the magnetic field, but this time the magnetic field is also sinusoidally changing. It's B naught sine omega t. So it's a time varying magnetic field. So here we can say Vm is the combination of the motional Vm that is caused by the rotation of the loop plus Vm transformer, which is caused by the time varying magnetic field. So this is produced by the rotating loop. This is produced by time varying B. Good. We just found Vm M. Vm M was B naught A omega sine omega t. But this B naught here is not only B naught anymore, it's B naught sine omega t. Okay? So this is, if you plot B here, it's going to be Vm M is going to be minus d psi over dt. And the only thing, we are going to consider everything to be constant. B is going to be constant when we are calculating the motional mth. And the only thing that is changing with time is the angle. So it's going to be bt a omega sine omega t, which is going to be B naught A, or B naught sine omega t A omega sine omega t. B naught A omega sine squared omega t. So you see, when we are considering the motional mth, we don't care about the time derivative of B, t. We are assuming, just like the product derivative of two functions, basically, we are considering bt to be constant. That's why we can easily just plug it in here. Now, when we go to Vm transformer, now we are going to consider the other two variables to be constant, and the only thing changing is the amplitude of B, which is going to be minus d over dt of amplitude of B, A cosine omega t, which is the angle cosine alpha here. So this is going to be minus d over dt of B naught sine omega t, A cosine omega t, which is going to be minus B naught A omega cosine squared omega t. Yes?
Instead of doing this, we have just multiplied B and alpha, like the two expressions, and then taking derivative.
Yes, like a mathematician. Yes, this is the kind of like just explaining the physics behind it, right? Remember this. We had one slide here. Remember here, we said in the general form, we can write psi as the function of b dot ds, and we called the first term to be VMF transformer, the rest of them were motional, right? So we are just doing that, but this time a little bit maybe different. But you could totally do the same thing. Okay, so now let's find the VMF total, which again we said it's a combination of the summation of both the motional one plus the transformer one. This is going to be minus b naught omega cosine 2 omega t minus sine 2 omega t. Do you remember what is this identity? Cosine squared of x. Yeah, exactly. Cosine squared of alpha minus sine squared of alpha is cosine 2 alpha. So this is going to be cosine 2 omega t. So minus b naught a omega cosine 2 omega t. Let's take a minute to see what we just did. We were rotating a loop with the frequency omega. We also were changing a magnetic field by the frequency omega as a sinusoidal wave. Both of them are being general sinusoidal functions that are changing with the frequency omega. And all of a sudden now, we created a voltage source that is changing with the frequency twice omega t. Right? We doubled the frequency of the change that was happening in the rotation of the loop and also the change in the magnetic field. And that helped us to create a voltage Vt that is 2 omega. It's changing by 2 omega. Okay. What is this one? This is the same. Okay. Any questions? No? Everything is clear? Okay. There's not much left from the course.